Hey guys,
Hello.
we're going to jump back a few sections because we need to talk about inverses before we move on to logarithms. So here we go. Inverse functions. When we reverse, exchange inputs and outputs, that's your independent and your dependent. When we exchange those values, we have what's called an inverse relation. Now, if that inverse is a function, then we have an inverse function, and that's what we're going to be talking about today is when do you have something that's an inverse function. Everything that can be graphed has an inverse relation because all you're doing is switching the x's and the y's.
Swap.
Yep, swap them. So everything that can go on a graph can have an inverse because you're just switching the x and y's to get the inverse, but not everything is a function. And that's going to be our purpose for today. Now on your notes, it does not have the parabola drawn there, so you have been given the points. So while we write down what the points are, because we're going to do something with those, go ahead and plot those points. Negative 6, 5.
Pause the video, and as soon as you get back to us, as soon as you're done, come back and we'll graph the inverse
Okay,
with you.
good.
Alright, so hopefully you pause the video, and here we are. We have our function points here. We're going to write the...
Yeah, those the blue points there, that's our f.
That's our function. Now we're going to write the inverse relation.
And we're just going to call that g for now. Okay, so if you switch the x and the y, negative 5, 6 becomes?
5, negative 6.
Yep. Negative 5, 0 becomes?
That's a negative.
0, negative 5. Negative 4, negative 3 becomes negative 3, negative 4. And negative 3, negative 4 becomes negative 4, negative 3. Negative 2, negative 3 becomes negative 3, negative 2. Negative 1, 0 becomes 0, negative 1. And 0, 5 becomes 5, 0.
Swap!
And now we're just going to go over here and we're going to plot these points. So if we plot 5, negative 6, 0, negative 5, negative 3, negative 4. Hey, look at that. Shares a point. Negative 4, negative 3. No, negative 3. Oh, shit, I'm silly me. Yes, you're right. I was wrong. I'm counting wrong. Doing what students do. Negative 3, negative 2. 0, negative 1. And 5, 0.
All right.
Yeah, connecting these will be, oh, wow, that's good. That is clearly not a function. But it is an inverse relation. Why? Because we inverted the x's and the y's. But the cool thing that you should notice is if we can draw it, we're trying to draw what is called the y equals x line. Okay? And the y equals x line is that diagonal line that goes through the origin. And when you have your x and your y and you switch your x and your y, notice that that function reflects across the y equals x line. And that is always going to be a feature of functions and their relations.
All right. So, if f is a function and AB is a point on f, then the swapped point, BA, is the point on the graph of its inverse. So, basically, an inverse is reflection across the line y equals x, which you just saw. So, how on earth would we find an inverse? Well, write the function in terms of x and y and swap the x and y, and then solve for y. I would do my karate move, but you wouldn't see it. So, here we go. I'm going to find g of x, the inverse of f of x. So f of x I'm going to write as y equals 2x plus 1. And now I have to swap! Swap! That doesn't look like, there we go.
Yeah,
Swap the x and the y. So now I have x equals 2y plus 1. And now I have to solve for y. So.
That's just an Algebra 1 concept.
Yay, I can do that. I can do that. Let's see, I have x minus 1 equals 2y. Divide both sides by 2. And that gives me y equals x minus 1 over 2.
But, yeah, and that's a really good, and you could actually write that, you could recognize that's going to be y equals 1/2 x minus 1/2. But for the purposes of what we're doing, this is perfectly fine.
Ooh. Anyway, all right, so there we go. We've found I have attacked it. Okay, so we have found the inverse. I could rewrite it. Well,
That's good enough. Yeah.
Okay, that's good. All right.
Now this one, get ready for this one. This one's got a lot of details to it, so it's going to have a place in the middle where it's really funky. All right.
So here we go. We have f of x equals 4x squared minus 2x. So I'm going to rewrite it as y equals 4x squared minus 2x. And swap! Here we are. Swap. X equals 4y squared minus 2y. Now, I have to solve for y, because that's the goal here, is to find g of x, okay? So,
Ooh, y's quadratic. What should we do?
we can use, well, I can't factor it.
No.
So, I'm going to go ahead and use the quadratic formula.
Which means setting the whole thing equal to 0.
So I have 4y squared minus 2y minus x equals 0.
Mm-hmm. Now this is weird because if we're going to use the quadratic formula, we have to be able to actually find our a, b, and c. So a is easy. It's 4.
A equals 4.
B is
negative 2.
C, unfortunately, remember we are solving for y. So when we're doing that, guess what? That x is a constant. So C is actually negative x. I know that's a kind of a weird concept, but now this gets really, really crazy. And here we go. We're going to substitute into our formula. First step is total substitution. Y equals negative b
plus minus square root of quantity
B
squared
Here,
minus 4ac
AC
negative x. All divided, I'm going to get it over there.
by 2 times A. Okay, notice that's a plus 2 up there because that was the negative of negative 2. Now we're going to do a little bit of work, so that gives us 2 plus or minus underneath the radical. That all becomes 4 plus 16x. All of this is over 8. Now, what you might notice here is you've got a common factor of 4 under the radical, which when we take the square root comes out. So let's factor the radical. 2 plus or minus 4 times parentheses 1 plus 4x. All of that, oopsie, 1 plus a w, 4x, all of that is over 8. Now that 4 underneath the radical becomes a 2 outside, so we now are looking at y equals 2 plus or minus 2. 1 plus 4x is under the radical. All of that is over 8. Still have to extend. That's crazy. Factor out a 2. Y equals 2 times parentheses 1 plus minus square root of 1 plus 4x all over the 8. And now you can cancel and we get our big magic ugly answer. Y equals 1 plus or minus the square root of 1 plus 4x all over 4. And we can refine that a little bit. When you get into another math class called calculus, you'll actually do more with that. But right now, that's all we're going to do. And that's ugly and gross, but that would switch our x's and y's, and we would be able to find out what the other graph would look like with that information.
Now notice in example 2, y really is a function, okay? But in example 3, we've got this plus or minus business that would make it not a function.
Yep, that's a good point.
So here we could write g of x equals x minus 1 over 2, but in example 3 we couldn't write g of x because it's not a function.
Well, we can call it g of x. What we can't do is give it our special function notation. But you're right. We can't write, well, no, we can't write g of x because
function notation.
There we go. We can't. Yep. Even though in the book they do that, sadly. Okay.
It's illegal. Okay, so for your ET problem 1, go to section 3.6 and work 2, 3, 10, 14, and 18. All right, so determine whether an inverse is a function. Every output must correspond to exactly one input, making f a one-to-one function. What does that mean? Well, a function is one-to-one if f of a equals f of b implies that a equals b, which means you can't have two y values go to the same y value go to two different x values.
Yeah, if you have two y values that are the same, if the y values are the same,
then the x
then they had to have the x values. That's what it means, the same x value. That's what it means to be one-to-one. But next part's really cool.
If a function is one-to-one, then its inverse is also a function. Okay? So, we know a function is one-to-one. A function is one-to-one if it passes the horizontal line test. That means that if it's a function, it passes the vertical line test. If it's one-to-one, it passes both, the vertical line test and the horizontal line test.
And the cool thing about that is, if a function, call it f, passes the horizontal line test, then its inverse, when we go to graph it, will also be a function. So that's kind of cool, and we get to use a special notation. We'll talk about that in a little bit.
So like this one passes the vertical line test, but it does not pass the horizontal line test. All right? Because it's got two values that equal the same y, two x values that equal the same y value. But then we have this guy over here. Oops. We have this one right here that passes the vertical line test, and he passes the horizontal line test. So since he passes both, he is 1 to 1. All right, so his inverse would also be a function.
Now we're going to look at some graphs, and each one of these graphs, we could have made an XY chart, but we're just going to use the graphing calculator. So the problems you'll have to work on this right now will be involving graphing calculator. So here's our function f of x equals, you can see what it says. Now, notice that f passes the horizontal line test, and we like to just write HLT because it's easy. That's what HLT stands for. Therefore, those three dots, if you've never seen that, that means therefore in mathematics, it's 1 to 1. And when we write 1 to 1, we usually do it like that with the dash. So what does that mean to say that? It means that its inverse is a function. Okay. So there's a couple of points we can see very easily. One is the y-intercept of our function f. That is the point 0, -2. And by using the solve feature, we can find that the x-intercept that we see is the point 0.80. And if we switch those, because x and y switch when we graph an inverse, 0, -2 is going to become -2, 0, and 0.80 is going to become 0 and 0.8. And your graph is going to look something like this.
That way. La 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 la. Gotta graph it. Gotta graph it, kind of.
Yeah, kind of looks like that.
It has a little bumpy. I'm not so good.
And if you were to sketch in the y equals x line, you would see that it would just go, it doesn't go from corner to corner in our graph because our graph's not a square, but you would see that the line pretty much just does from here.
Boom, 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 boom.
And here's what's really cool. Where it intersects the y equals x line, so does the other one.
So that you can always draw the y equals x line through the intersections if you have them. Which is kind of cool.
Okay, so some observations. Note that f is always increasing. So it passes the HLT, the horizontal line test, and it is 1 to 1. And its inverse is a function that is also always increasing. Kind of cool.
Okay.
Okay, next one. We're just going to look at a few functions. Oh, look at that one.
Ew. But we know that it goes through 0, 1.
But we could graph the inverse relation, but here's the thing. The point is, G does not pass the horizontal line test. Okay? And since the instructions say to graph the function and determine if it's 1 to 1, G does not pass the horizontal line test, therefore it's not 1 to 1. Therefore, its inverse is not a function. And that's pretty much, so we don't have to do any more work. We could graph the inverse, but we don't need to. Note, G is decreasing and increasing. So anytime you have a function that is decreasing and increasing, it is not going to be 1 to 1.
See, it's increasing from about -1 to 1, right in there.
Yeah, and it's decreasing on the other
Everywhere
intervals.
else.
So it does not pass the horizontal line test, and it is not 1 to 1.
All right. So here's the next one. H of x equals -2 minus 0.8 x cubed. Okay. So as you can see, H passes the horizontal line test. There we go. Therefore, it's 1 to 1, and its inverse is also a function.
Let's note the direction. What is our direction of H? It is always decreasing. So since it's going one direction, it's going to pass the horizontal line test. it's 1 to 1, as we pointed out above. And so the inverse will also be decreasing. That's a neat little property that functions in their inverse have. And we can do a little sketch of it. Again, it's pretty easy to see that the y-intercept is the point 0, -2 in this problem. And using the solve feature, we can find that our x-intercept is about -1.40. So its inverse point would be
0, -1.4.
0, -1.4. And this one's kind of easier if you kind of sketch the y equals x line, but it's going to look something like this. Remember, if f is decreasing, which is our f1 here, but it's h in the what we printed, if h has to be decreasing, its inverse is decreasing. That's a nice little property. Okay, and again, if you sketch through, the cool thing is if you do the y equals x line, this point right here will have to lie on the y equals x. That's a really important thing. Okay, so we have the general idea of what these things look like, so please go
to section 3.6 and do 24, 25, and 26.
All right, some math terminology. TFAE means the following are equivalent. If you ever pursue mathematics, you'll see that somewhere down the road. All right, the inverse of a function of f is a function also means f is 1 to 1, also means f passes a horizontal line test. So if we were to say f is 1 to 1, then we would know its inverse is going to be a function and f passes the horizontal line test. So that's what the following are equivalent means. Stating one of those implies the other two are true. And once we've established that we have an inverse function, we get to use special notation. And this is really important that you see this notation, because this f to the -1 is very important. It does not mean this. Okay? This notation -1, when applied to a function, does not mean the notation that you're used to. That's really important to pay attention to that.
All right. When a function is not 1 to 1, you can sometimes create an inverse function by restricting the domain of the function to the part that is 1 to 1. So, for example, if I have a parabola, notice it's not 1 to 1. However, if I say, oh, I'm going to keep it, my domain is only going to be from this point up on this side, then it's now 1 to 1 because I'm ignoring this part. Okay? So, we can restrict a domain and make a function have an inverse that is a function.
So we're going to start with a parabola, and look at that. You can see that x squared minus 3, you should know that's the parabola, y equals x squared shifted down 3. And so we know that. And we know that because its vertex is going to be on the y-axis, we know in this problem, let's just sketch the graph. If we restrict the domain for values of x that are 0 and bigger, then we'll have 1 to 1. So if we sketch the graph, this is putting in values for x from 0 to bigger than 0. Okay? And now that allows us to have, we can talk about that graph right there having an inverse that is a function. Remember, every graph has an inverse. The question is the inverse a function? So if we list our points on f, the points we had, oh yeah, restrict a domain of f to 0 to infinity, then f is 1 to 1. Let's just write down some points that we found really nicely and easily on f. We had the point 0, -3, 1, -2, and 2, 1. So on the inverse,
I graphed 3, 9 as well.
Oh, you're such an overachiever. Okay, now we already know that since we've restricted our domain, we're going to be able to make this inverse a function, so we're going to use the notation f inverse. And again, switch the x and the y, so -3, 0, -2, 1, 1, 2, and 9, 3, which we don't have room for on the graph, but that's okay. -1, -2, 1, 1, 2, and 9, 3, which is way off the board, but you get the idea. And there we have it. And once again, if you sketched, can you sketch the y equals x kind of dotted in green maybe? The y equals x line would go right through that, and notice it's going to go right through that point and all the way down, and so you can see that we have a reflection across that. Now, if we want to find, it says to find f inverse, so what we need to do is actually find it. So y equals x squared minus 3, and we do what?
Swap! So we have x equals y squared minus 3.
And solve for y.
3. So x plus 3 equals y squared. Square root. But
wait, let's write the proper thing. Y equals, let's do the proper math, plus minus square root of x plus 3. However,
we are only taking the positive values.
So we're only taking, this is a cool thing, we're only taking the positive values for, the positive values for x here, which is going to mean our y will only have positive values. So we're only going to take the positive part. So y is equal to the positive values of x plus 3. And now that we have established that's going to be a function, we can write it like this. So this is where you really have to start thinking about the work you're doing. It's no longer just a rule, it's thinking about what's happening.
You must remember these things. These are important things to
they really are. Yeah, they really are.
All right, try section 3.6, number 38 and number 40. Okay. The inverse of a function sends each output back to the input it came from. That is, if you have f of a equals b, then f inverse of b equals a.
Now, a good way to think about this is that when you have your x coordinate a, it becomes y. So on the inverse function, remember that your x becomes your y, and your y on the f function becomes your x. So notice that this notation is saying under the inverse operation, we're going to take the y coordinate that was and send it back to the x coordinate that was.
This is kind of like shopping. You go to the store, you give them money, they give you a shirt. If you don't like the shirt, you go back to the return and you get your money back. So,
if you have a receipt. Ha!
Yeah, well, yes. So, the input is money, you output a shirt. Now, when the return, the inverse function, is you return the shirt and you get back your money.
I like that. I haven't heard of that one. That's a good use. All right, now let's look at some notation that's really important. I don't know if you remember compositions of functions. We did that a way back ago in chapter 3. Notice that this little circle means f of, so we're looking at f inverse of f of x. Can be written like that, and it's going to give us x. Also, we can go f of f inverse of x, which gives us this, which gives us x. Now, I'm going to say something right here. I'm not going to confuse you. I'm going to just try not to confuse you. In a little bit, when we get to trig functions, there's actually a special law we have to pay attention to, because some of this is not always true when we start thinking about trig functions. But in general, if you take a function and compose it with its inverse, you're always going to get x.
Okay.
So now, here we have f of 3 is 10. So
I bought a $3 shirt and I got $10.
And so, so
I take the shirts back and I get
$3.
3.
So that's the answer. So another way to think about this is the point 310. F of 3 equals the point 310 on f is the point 103 on f inverse. So function f, just write an f over. Okay, no, I was going to say put the f there. Function f gives us this. F inverse, come down here and write f inverse, moves it back.
Oh, okay. This is f inverse.
Yes.
Okay.
All right. So let's see if you can do this one. What do you think is going to happen?
Pause the video. Yay, you did it. I hope. If you said 7, you are correct.
There you go. All right. So let's see how to prove that two functions are inverses. Okay. We notice that it says to use composition. So that's not what we've done before. Earlier in the video, we found your x and your y and we swapped. Now we're going to compose, and you have to do both sides of it.
We're verifying.
We're verifying. So here we go. We're going to first of all write f of g of x, which we know means f of g of x, which is, in this problem, f of 3x over x plus 2. Now this looks horrible because what this means is 2 times 3x over x plus 2.
I'm trying to help you out here.
Yeah, that's very good. Over 3 minus 3x over x plus 2. Now you're looking at this going, oh, gag. All right, let's remember we have a little SAT trick. First, on top, we can just multiply the 2, so we get 6x on top. On the bottom, we get x plus 2. Now, that's on the bottom of the top fraction. On the bottom, we can do this. The little SAT trick, you'll notice that this is over 1, so we do 3 times this. Notice that's in parentheses, so 3 times parentheses x plus 2 minus the 1 times the 3x over this times this, 1 times x plus 2. Now we have some work to do, so rewriting that fraction gives us 6x over x plus 2 on top, and on the bottom eventually we get 6 over x plus 2. Again, check the work up here, distribute the 3. This is 3x plus 6 minus 3x.
Minus 3x.
So the 3x's drop out. Now, notice what you have here. One way to look at this is you've got 2 common denominators, x plus 2 and x plus 2. But if you don't see that, write it as 6x over x plus 2 divided by x plus 2 over 6.
No.
Divided by 6 over x plus 2,
2.
excuse me, I'd already flipped it. Yeah, which is equal to 6x over x plus 2 times x plus 2 over 6. You can surely see what cancels, and probably need to extend the page a little bit. And we get finally that what we were looking for, f of g of x, did give us x. Now, the sad thing is, you have to do the other side as well. So this is just the showing f of g of x equals x. Now we have to do g of f of x equals x. So here we go on the next side.
I'm going to make it all smaller. Grouping group. Make it smaller. Hopefully you got what you needed.
Okay, so now we need to look at g of f of x. Which means g of f of x. Which means g of 2x over 3 minus x.
3 plus 2 parentheses.
And so 2x over 3 minus x is what our new substitution is.
2x over 3 minus x.
And once again, following our SAT trick makes this fraction become 6x over 3 minus x. All of that is over 2x plus 2 times parentheses, 3 minus x, don't forget those parentheses, all over 3 minus x. Do a little algebra, we get 6x over 3 minus x over 6x over 3 minus x. And that would, hopefully you can go on to the next step, that is actually 6x over 3 minus x.
Oh, you said 6x. I was like, what? Okay, this should be 6.
Oh, that should be 6. I'm sorry, my bad. I'm reading the fractions wrong. 6 over 3 minus x. So going to the next step, of course, you could write that as the division, but hopefully you could go straight to 6x over 3 minus x times 3 minus x over 6. You can see what cancels.
That goes.
Whatever.
All goes.
And we get g of f of x equal to x. Now, therefore, we have shown f of g of x equals x. We have shown g of f of x equals x. Therefore, f and g are inverses of each other.
There. Okay. So, go to section 3.6 and do some composition. La la la!
Now remember, you're not swapping here. You have to do this by composition.
Okay, so to confirm that you have watched the video, email your teacher by 8 a.m. the day of class with following information. 1. The subject line of your email should be 3.6 video with your class period. Okay, so in parentheses next to it should have class period.
Yeah, don't type class period.
Yeah, type the one you're in.
A2, A3, B2, etc.
Yeah. 1 new thing you learned, 1 good question, and 2 old skills that are important to recall for this material. Don't forget to bring your entrance ticket and completed notes when you come to class. Thank you.
Love you.
Bye.